All right, so today we're continuing with our ensemble methods, and more specifically, we're talking about our boosted algorithms. So on Monday, we talked about bagging algorithms, which are also a subset of ensemble methods, but today we'll be talking about a different class of algorithms known as boosted algorithms. Boosted algorithms, again, a subset of ensemble methods, and today we'll be talking about two main types of boosted algorithms, namely, oh, this is brighter than I thought, namely AdaBoost and gradient boosting. So we'll talk about both of those methods, and we'll also briefly look at one more called XGBoost. So we're going to look at the difference between bagging and boosting, as well as these two specific methods. And both AdaBoost and gradient boosting are methods that are cyclic methods. All right, so boosting overall, this is the intuition behind boosting. So it refers to any ensemble method that combines several weak learners and their mistakes into a strong learner. So remember how in bagging, what we were doing is we were training multiple versions of the same model. Remember with bagging, we were bootstrapping and aggregating our data to create bagged trees. And what that means is you're just like sampling with replacement. You're just using different subsets of your data to create the same tree with different data, and then doing like sort of like a voting or an average to classify. Instead of that, boosting uses their mistakes to improve the algorithm. And we'll talk about the different ways AdaBoost and gradient boosting does that. The general idea of most boosting methods is to train predictors sequentially, each trying to correct its predecessor. So again, it's just this whole idea of, all right, I trained this model. Where did this model go on? How can we make it better? And we're going to focus on what was misclassified. So again, many boosting methods available. If you look up like list of boosting algorithms, there are a lot, but the main categories are AdaBoost, which is short for adaptive boosting, as well as gradient boosting. So this, I think, is a really neat diagram to showcase the difference between bagging and boosting. Color's not the best, in my opinion, with this green and purple, but single model is this one here. You just have one iteration of a model. You're fitting, for example, a decision tree. You fit one decision tree, and that's how your model works. Bagging, as we talked about on Monday, you're training in parallel. You're training a bunch of different versions of the same model on just subsets of the data. So with bagging, you're bootstrapping and aggregating your data sets, feeding the new data sets into the same model, and doing some sort of aggregation of that. With random forest, of course, you introduce some additional randomness by choosing a subset of features at each split. Now you see how the arrows for bagging are each input goes from data to model, data to model, data to model, and none of these are connected to each other. Whereas in boosting, you start with your data, feed it into the model, you take the output of your model, do something with the output of the model, usually what has been misclassified or what was wrong, feed it into a different model, or sorry, feed that into a model but in a different way. And you're basically feeding the outputs of your previous models into new models. And so it becomes a sequential approach. So the main difference is in bagging, things are done in parallel. In boosting, you're sort of layering models on top of each other. You're going to take the output from one and then put that into the next in some form, which we'll talk about in a bit. But questions about this?
Yeah, what do you mean about feeding it in a different way? Is it using different features?
Yeah, absolutely. So the two methods that we'll be talking about, AdaBoost and gradient boosting, we'll outline the different ways in which it uses the mistakes and feeds that into the new model. So we'll get into that in a little bit. But yeah, that's good intuition.
Yeah, I just want one clarification. Who was talking?
Sorry. Yeah, it was me, Henry. Just with the bagging, you have these parallel models, and then you just choose. Yes, you do the statistics on each one, and you just choose your favorite, correct?
Not exactly. So let's say you're training all of these different models. Let's say we're classifying if something is poisonous or not. With all of these different models, you might, if you feed in a data point into all of these models, you're probably going to end up with somewhat different results for each model. And then the idea is most of the time you'll just pick whichever one most models decide. So you're actually going to make use of however many decision trees are part of this bagging model. So you're not picking your favorite tree, you're going to be using all of them together.
Okay, one clarification I wanted. Can bagging and boosting be added as the hyper? So when we get into the hyperparameters, when we put the details on the hyperparameters,
Yeah.
can these work when we are writing the function for the model and we just add it as an hyperparameter?
Yeah, kind of. So these are not added as the hyperparameter. So by default, bagging and boosting are both using decision trees. So you're actually going to be using bagging and boosting. So for example, if I do, let's see, I think it's bagged trees, scikit-learn. There we go, bagging classifier. It's going to be a separate model, a separate scikit-learn model that you instantiate and import. And the main thing that I want to point out here is, I think I pointed this out last time as well, base estimator is going to be what is built off of. And so here, the base estimator is a decision tree by default. So if you wanted to use like KNN as your base classifier, you could do that as well. Might not be as effective, but yeah, you can definitely feed in different classifiers into this like base estimator parameter. That could be something you tune as well, but by default, people use trees. It's going to be the same for AdaBoost. So just to show you this first so we can compare. Yeah, this is the one. Again, you can see as part of AdaBoost, the base estimator here is a decision tree classifier with max steps of 1. So they're just going to be doing this over and over and over again. And again, I'll talk about why this max steps is 1.
So yeah, so when we talk about max step 1, it's only one layer, or it's like
it's a one layer tree.
Okay.
Yeah, and I'll talk about why that probably is the case for later. But yeah, questions so far regarding like differences between bagging and boosting. So they're actually like, they're really using the exact same model, just differently. So yeah, we'll get into like what this process of like going from model here into like that looks like. But yeah, other questions regarding this? All right, so hold on, let me rearrange my screen a little bit. Okay. All right, so boosting models, it's a statistical framework where the objective is to minimize the overall loss. Loss is just another word for cost function. Is to just minimize the loss of the entire model by adding weak learners using a gradient descent-like procedure. So gradient descent by itself is optimizing the performance of a single model, right? Like gradient descent itself is trying to make a single model best as it can perform. You can sort of think of this process of boosting as they're performing gradient descent with model after model. So they keep adding models to slowly decrease your overall error. I know it seems pretty abstract, but the ways in which this works, we'll get into details in a little bit. So you can actually use different loss functions. That's actually a hyperparameter that you can tune. I believe here, yeah, you can use different algorithms. You can use, yeah, not so much this one, but I believe the one that we'll talk about at the very end, you can actually say, you can actually say what kind of loss function you want it to optimize over. So boosted algorithms are not only for trees, as I mentioned, like base estimator is something that you can change up, but it's also a general procedure that other classifiers can perform. So if you wanted to do your boosting on a different algorithm, like for example, maybe KNN, or you want to do that with Bayesian classification, you can potentially do that as well. But typically it's done with trees. All right, so the intuition of AdaBoost. So this is just a picture version of AdaBoost. It's going to train one model first. So let's start here. We have this original data set here. And as it trains the model, this is the trained model. Imagine that this is the classifier now, that this is the new division line. Here you can see that we have 3 points that have been misclassified. the way that AdaBoost works, with these misclassified points, it's going to update the weight of these points. So for example, it's going to maybe like double up or triple up on these points, so that it's not super clear in this diagram, but these two minuses and this plus is supposed to look bigger. So with that, you're going to focus in on these points were misclassified. Let's make these more obvious to the model so that the model can retrain itself based on that output. So as you can see, it's still kind of the same data, just that, well, these are supposed to look bigger. These two minuses that were misclassified and this plus that was misclassified, it's supposed to look bigger, and it's supposed to look bigger to the model, supposed to be more significant, such that the model is more sensitive to those previously misclassified points. And so that is actually done repeatedly. So with these updated weights, apparently the new train classifier puts a split over here, figures out, all right, these are what's being misclassified now. So let's emphasize these three minuses now in this example and retrain a classifier again. And then you're just going to keep stacking all of the results of these individual small models. And that's the reason why I think, you know, you're using a depth of 1, because you're just going to figure out, okay, at each step, what's being misclassified, and then improving upon that. And so even though, you know, it's a tree of max depth 1, if you have multiple trees of max depth 1, and after each split, you're learning what was misclassified, you can combine all of those together and have this combined classifier. And maybe you have like, all right, these 3 boundaries were created. Let's just overlay that on this diagram and take a look and see, you know, how to use the combination of all those weak learners together. The whole intuition to AdaBoost is, and actually to any boosting model, and we'll talk about how that works with the other one later, but you tell me what didn't work, and I focus more on those data points. So points that are easy to classify, like all the points that were correctly classified over and over again. So it seems like, I guess in this example, not really, but basically points that are easy to classify, the model doesn't need to look at because they're easy to classify. So you're just focusing the model onto what it's doing wrong. Questions about this?
One question. How do we identify with what is going wrong?
That is all done in the model. Is done in the model for you. So when you literally run AdaBoost, you do AdaBoost.fit, it is doing all of that for you. And you tell it how many, let's see, yeah, you tell it how many times to boost, and that's what it'll do. So by default, it's gonna do this 50 different times. And yeah, and in case of perfect fit, the learning procedure will be stopped early. So yeah, you can train you can do this process as many times as you want. You never have to do this manually, but behind the scenes, this is what is going on.
Okay.
Yeah.
To follow up on his question, I guess you're basically feeding in test data at the same time you're feeding in the training data, and that's what it's the target. Yeah.
Absolutely. Yeah, we're gonna get into more details in a little bit. Yeah, but yes. Cool. So again, just to put into words what I pretty much described earlier, first you initialize the weight of each of the observations. Typically, every observation is going to be weighted the same at the very start. You're going to consider every observation equally. Then you fit your base classifier, and then make predictions on part of the training set. Or actually, no, you can make predictions on the training set, and just it's basically your overall training accuracy. Like for example, if you were to print the confusion matrix for your training set, that's what it's fitting on. It will increase the relative weight of the instances that were misclassified. So basically what was going on here, you know, we're magnifying this plus and these two minuses that were misclassified. So the model will consider those points more. And then train another classifier. Usually it's the same classifier again, using the updated weights of your data set. And then you're going to aggregate your classifiers into one, weighting them by their accuracy. So that's the process of putting the different models together. So let's say this is not a good thing, but same thing. Imagine this classifier was only 10% accurate. Well, actually, let's see, there are 10 points here. So this one was 70% accurate. This one was 70% accurate as well. This one ends up being, I don't know if this counts, but I guess this looks less accurate now. This one is about 60% accurate. And so you're just going to weight them based on that, and then feed that into your classifier. Feed that into your final model. And so your final model will be a combination of all your classifiers. So kind of like it's the way it aggregates, it's still going to feed your data points into all the classifiers, just at a different weight. So the result of your classifiers will be weighted by how accurate it was on the data. Other questions? Okay, the next slide is math. I'm going to skip over this slide because for us, we don't need to know this right now. Pretty much telling us the same thing, but we don't need to get into this. So something that's more specific about this AdaBoost model to prevent overfitting as well. The first classifier is trained using a random subset of the overall training set. And because of this random subset, that again just prevents the overfitting. And yeah, and again, same misclassified items, assign higher weights so that it appears in the next training subset of your classifier with higher probability. So what's happening is in this diagram, you can sort of imagine, all right, instead of, so I guess in this population, there are 10 data points and you're doing that over and over again with these 10 data points. What's happening in reality to prevent your overfitting is you're going to actually sample with replacement your new data set. And so what happens here in these 10 points, maybe you're saying, all right, each of these points is going to double because, you know, these are misclassified. To create this next set, you're going to randomly sample 10. And so therefore you have a higher chance of these points coming back up, if that makes sense. It's the same as bootstrapping actually, but just the weights of each observation are changing based on whether they were misclassified in the previous iteration of the model. Questions about that? I know it gets a little bit abstract. Boosting models specifically is one of the harder ones to understand in depth, but it's the idea that, you know, you're just improving upon your model by modeling by just taking note of misclassified objects. All right. This one is just a weighting of the classifier. We'll also skip over this because this is more math. And finally, AdaBoost also works for regression. AdaBoost has a regression counterpart, and differences very, very minor. So basically, both of them start with weak trees. In classification, we talked about misclassification penalty to determine the weight to modify predicted values. So basically, that's the whole idea of, you know, you're going to weight higher anything that was misclassified. For regression, if you have, because imagine for a regression, you're predicting on a continuous variable. Because of that, you can use your loss function, and in your decision tree, in your regression, it's actually an RMSE. If you remember, I don't know if y'all remember regression trees, but the cost function of a decision tree is also sort of an RMSE. A regression tree is an RMSE, sorry. And you're going to use that to determine how to re-weight your misclassified error. So it'll actually be re-weighted by the RMSE of your points, which is pretty cool. And then that's the only difference in the rest of that. You're just going to create new trees and then use all the trees together. Questions regarding this? It's more of like a summary. Nice. Now, something else to consider, data preparation. When you're doing boosting, if you're thinking about your boosting, how should you consider your data, right? First, the quality of your data, because your Ensemble method continues to attempt to correct misclassifications, you have to be very careful that you have high quality training data. If you have, for example, like typo, like for example, that example with 33 bedrooms in your regression problem, that could bias your classifier, because, you know, it might see that, all right, this is a misclassified thing that I should really look at, you know? So if you have if you have wrong data, you don't want it to learn from those mistakes. Similar for outliers. Our outliers will force the Ensemble down the rabbit hole of working hard to correct for those cases. So you should look to remove outliers from boosting models. Because if you imagine, things that are misclassified are likely to have outliers, right? I mean, typically a reason that things are misclassified because they are outliers. Maybe they just have something that the model hasn't recognized before. You don't want your model to learn those nuances typically. And finally, noisy data. It's kind of the same concept as quality of data and outliers. If you have noisy data, you don't want your model to overlearn this noise. It also will lead to overfitting. So questions so far? The next slide is going to be a summary of AdaBoost. Nice. So sequentially trains classifiers. It improves the classifier by increasing the weight of misclassified instances. Yeah, talked about that. And then to put the classifiers together, you weight them based on their accuracy. And then you aggregate them. And also finally, does it perform well on noisy data and outliers? And you can also use it on any type of classification model. So that closes out AdaBoost. The next,
Yeah. One quick question. How do you differentiate between noisy data and the outliers?
I sort of think of noisy data as like if you have a lot of if you have just inconsistencies. So outliers is something like, you know, if you plot like your histogram and you have like one point at the very end, that's an outlier. Yeah. But if noisy data is just like something that isn't just, it's just not consistent. Like for example, maybe you are trying to find the price of a house, but you're also considering as price of the house, maybe you're considering factors that are really random, like, I don't know, what kind of, I don't know, the number of, I don't know, I can't think of anything random enough, but maybe you're considering the color of the mailbox of the house that is like, should not affect the price of a house, but you're including that as well. And so that could potentially just lead to weird patterns that are being learned.
Okay.
Yeah. That's a good clarifying question as well. But yeah, so after AdaBoost, we have gradient boosting. Gradient boosting actually works extremely similarly to AdaBoost. Just a minor difference that we will look at. So just like AdaBoost, gradient boosting evaluates a collection of trees sequentially, and then Ensemble is a collection of trees that model underlying behavior of data. However, the main difference is the gradient boosting models evaluates the residuals of the previous tree to predict the residual. And so it actually uses a gradient descent like procedure to figure out the next best model. Let's not worry about the math for now. But imagine we have this data and we want to just classify this data. So we have this scatter plot that's pretty messy. Gradient boosting, how it works and how you think about it is you're actually going to look at the residuals after each model. So I don't know if y'all can see it. Let me know if it's too small. At iteration 1, let's say you are training a model that predicts these points like this. And so the red line is going to be your predictions. With your red lines being this prediction over here, it's going to look for your residuals. And so your residuals are going to see like, all right, how far is each point from the line? I'm guessing this line over here is actually what should be 0. So let me like redraw that really quick. This line, oops, meant to draw a straight line. This line here should be the 0 line. And these are the residuals. So you can see at the start here, the residual is 0. And these are up, down, up, down. And what it's going to do is it's going to run the model on residuals, which is actually a really neat concept. So over time, your residuals start to get smaller and smaller. So you imagine if we're fitting a model to the residuals, imagine we're fitting this same line and we're trying to train a new line to go through these points. It already knows this bunch. It's going to slowly learn the rest of your model. So you can sort of see that overall, the residuals are getting better. They converge to 0. Questions about that? That's just more of the intuition to begin with. All right. So this is just showing like a validation error over the iterations of a boosting model. Typically, something that you would plot because you have to decide on the number of estimators or the number of trees you want to boost over. You would usually plot something like this. You would plot your validation error over the number of trees. So as you can see here, usually with something like this, when you're tuning your parameters, your hyperparameters, you'll take a look at what your error is. At some point, it will start to plateau off. And and then you would choose a good point where it starts to plateau off. And that, in this case, will be 55, and you'll have some model that fits it fairly well. All right, the effect of estimators with boosting models, the more estimators, the better your model will get. Downside, very, very easy to overfit. You imagine you're gonna figure out every little difference, every little residual that your model predicts, every little residual between prediction and actual value, and it's gonna try to keep correcting for that. So it's actually very, very prone to overfitting. So here you can see this is an example with 3 estimators. And with 3 estimators, you see it's really not fitting this curve. This is with 200 estimators, and you can see it does fit all the data points really well, but it does look like it could have some overfitting going on. You know, it's learning every single point patterns. Questions about this? So this would be something you tune. With boosting models, the main idea is to tune for overfitting.
Would you eventually try to smooth it out to a smooth line on the right?
Yeah, typically, yes, you would want something that looks smooth. Whether the best for bias variance trade-off is the smooth line or not, really recommend that you have this kind of graph where you're looking at maybe your train and test error. And this is more for regression. Again, gradient boosting can be used as a regression or a classification. Easier to explain with a regression example, but can be used for classification. It's good to look at, for example, your train and test RMSE. At some point, they will converge. And then with overfitting, your test RMSE is going to go back down. Does that make sense? So typically on an RMS, if you want to look at your train and test RMSE, let me see if I can draw this out. All right, so I'm going to draw it down here. And this is RMSE, so you want to get as low as possible. And let me just note that over here. Oops, I want to use this now. RMSE, and this is for like a regression example. RMSE, and let's start with orange as the training RMSE. With training RMSE, it's gonna always, or roughly always, decrease. So it's gonna have that kind of shape. That makes sense. With your test set, and I'm gonna do test RMSE in green, it's also gonna start really high, possibly start even higher than your train one. So your test RMSE is gonna kind of, usually test RMSEs are a little more like unstable, but your test RMSE is overall gonna go down to some point, maybe like somewhere, usually not that close, let me undo that. Maybe somewhere like here. And then as overfitting starts to happen, and let's just say at this point overfitting starts to happen, your model will be unable to generalize to your test cases, and your test RMSE will start going up again. So the idea is to try and find this point right here where your train and test RMSEs are close together and low. Maybe, I guess based on my drawing, perhaps you want to take this point here, depending on if you want like an overall higher or lower, I don't know. But yeah, you would do some cross-validation to just make sure as well. But yeah, usually this will be the shape of your train and test curves. Not just RMSE, if you were to look at accuracy as well, it will just be flipped, because for accuracy, let me just draw another one just so it's clear. Let's use a different color. Same color axes, different color lines. And let's do accuracy for, yeah. So accuracy would probably start pretty low and then increase all the way up to like 100 or 100% accuracy. For your test set, usually what happens is, you're going to start with very low accuracy at some point. It's going to go up. And then at some point when your model fails to generalize, your accuracy will go down. So that's why you have sort of like this sort of shape. Not exactly sure whether these lines will connect or not. Does depend on the model, but these will be like the rough overall shapes you will see when you're trying to feel how much boosting to do for a model. I hope that helped to clarify some things. All right, any other questions? All right. There's not too much left in this section. We're just going to finish off the last couple of slides. We talked about this. Overall, again, with the differences between regression and classification, you see that both start with weak trees. With regression, we're going to minimize this objective function, and the objective function in the case of decision trees was basically like this function here, the residuals. But here we're actually using log likelihood. Not important to know what that is for now, but just know that this model is being retrained on residuals. And that's the main difference between gradient boosting and AdaBoost. They both work actually fairly well because it learns a lot of intricacies about data, but has the tendency to overfit. And then with both, you can create new trees using gradients from your prior tree, or yeah, and then add it to your ensemble. Questions about this slide? All right. Oops. Let me go to the next slide. All right. Finally, I wanted to talk about XGBoost. If anyone's doing like reading about data science or like is looking at data science competitions, XGBoost always wins competitions I mean, it is a great algorithm. We'll talk about why. So XGBoost is a gradient boosting model. It is a kind of gradient boosting model that was developed by, I forget who developed it, but it was developed separately. It's a specific kind of gradient boosting, and XGBoost uses a more regularized model to control for overfitting. So whereas the previous boosting models we talked about were very prone to overfitting, the more you make it aware of what was misclassified, XGBoost has regularization embedded in it to control for overfitting. So here, XGBoost actually stands for extreme gradient boosting. And because of that, yeah, it just does really well. XGBoost refers to the engineering goal to push the limit of computation resources for boosted tree algorithms. I'll go into, I think, yeah, does that say it here? I think it actually says it in your XGBoost reading, how XGBoost does this, pushes the limit of computations. XGBoost actually also affects the way that your computer is processing your trees. And what it does is I don't know too much about hardware exactly, but it is actually parallelizing the processes of training your trees. So your trees actually train multiple at a time and overall faster. So yeah, that's the reason a lot of people use XGBoost. A couple pros and cons. XGBoost is not part of scikit-learn. It's actually its own library. The implementation is very, very similar. The one annoying downside is it doesn't take in the data frames like other classification models do. It's usually like just one additional step of like you have to just convert it into a D matrix. I'll send out an article that walks through that process later on, but yeah, that's one big downside. It's not part of scikit-learn. So I have been talking to a bunch of you about functionalizing your classification models. That's one exception to look out for if you want to use XGBoost. XGBoost pretty much always outperforms other models as well. Once you get more, for people who are more advanced and understand like cost functions and want to be, and like pretty much machine learning engineers are able to edit the cost function of XGBoost, which is pretty cool. And you can give it more parameters. This problem, this point, I don't think it'll make sense to everybody, but the gradient descent algorithm that it uses requires the cost function to be twice differentiable. I wouldn't worry about that for now. And also it has built-in regularization, which stops it from overfitting, which is a huge pro. Any questions about XGBoost? This is just like a one-off algorithm. The math that goes behind it is really complicated. I've tried reading about it. I understand like mostly how it happens. I understand the part of it that works just like gradient boosting, but the other parts, it's just very complicated. So it is one of the more advanced models. But yeah, questions about this? I would say just a neat one to try out. And because XGBoost is still built upon decision trees, as long as you understand decision trees, you can just say that XGBoost is done on boosting the gradient, the residual gradients of decision trees.
You said there's a competition. Like, are there competitions where people try to find the best model for a given data set?
Yeah. So Kaggle actually runs a bunch of competition. I can actually see if I can pull them out right now. When I was a student, what a lot of us do to like help us think about if we had a problem, if we had trouble thinking of a data set to do for our project, we would actually literally just look into these. These usually are very difficult data sets. You're not going to get good results. That's why they are competitions. But yeah, Kaggle always has a bunch of competitions that anyone can participate in. And all you have to do is they actually give you the data set, and they'll give you a train set and a test set. You will, and yeah, all you have to do is just build a model. Like for example, let's see what there is here. This is great. You get like $100,000, but Jane Street, which is an investment group, I believe, they will give you, I believe they want you to do, this is probably predicting the market. And yeah, if you can create a model that that predicts the best, I guess you can win money. Yeah, so in total there's $10,000, and you can like win it like that, $100,000. But yeah, Kaggle competitions are like, if you are a serious like competitive data scientist, which is a thing, a lot of times XGBoost with edited loss functions end up winning Kaggle competitions almost all the time. And so usually to start, people will start with XGBoost models and then just work on tuning those. But yeah, it's very, very intense, but has some cool data sets that people are looking into.
The Tanzania data is not from Kaggle. It's a different
Yeah.
So that's again there. So there are, I think, I mean, I saw Kaggle and the other one, but then there are, my cousin was telling that there are around at least 15 different companies he knows, right, who keep competition on data science.
Yeah, there's a lot of places that actually hold competitions. Kaggle, I believe, is the biggest one, but yeah, Kaggle. If I'm not sure, there was like a lab that talked about Kaggle in the last mod, but if you don't know it yet, Kaggle has a bunch of data sets that are free and public for use. So typically, like if you're trying to think of something to do for your project, a good place to start is Kaggle, and maybe you want to search with keywords. They have a lot of very interesting things in here. But yeah, the next thing I wanted to talk about really quickly was grid search. But does anyone have any last questions about boosting models? I think, yeah, at the end here, these are all resources that I will Slack out to you all later as well. All right, so that is boosting. As I said, like with boosting, I know I say that, I said that with these models, at the end of the mod, it's not realistic to know all of them, but the math that goes behind boosting, and yeah, I would say boosting is pretty complicated. A lot of like current data scientists also are not able to explain exactly like in depth how it works. So if you're able to explain the underlying model, like for example, the decision tree, I think that's good enough. And if you're able to, on a high level, explain what's going on with gradient boosting or ADA boosting, that's fine. I think that would be enough. I highly doubt that like first, second year data scientists are asked to know this stuff. All right, so finally what I wanted to talk about was just really quick grid search. Grid search, I'm not gonna spend too much time talking about because I think it's pretty straightforward. The lab that walks through it, which is literally I'm gonna open up right now, is pretty clear on how to implement grid search. But grid search is basically a way to help you choose parameters without having to run your model like 500 different times. So let's just like load up this data set really quickly. I think, yeah, I already ran this. So what this is the wine quality data set, and what we're trying to predict is the wine quality. So let's just take a super quick look at df.quality, and I just want to look at value counts. All right, so this is going to be a multi-class classification, 6 classes, and we're going to build a classification model and try and figure out which parameters are best. And we're going to use grid search as a quick way to help us, or not quick, but as a less code intensive way to figure out the best parameters. So really quickly, this is what our data set looks like. I think for our purposes, it's not as important. What we're going to do here is we're going to do a grid search on decision trees. So procedurally, what you're going to do for your project or for your mini project as well is you're just going to run, typically what people do is they run the vanilla versions of as many models. I'm going to say that for this upcoming project, I want to see at least 4 models, but syntactically, they're all the same. So run as many as you want. And then for the vanilla models, and what I mean by vanilla models, the default models, so the models with their default parameters, the ones that perform best, like the 1 or 2 that perform best, then I would say go and do grid search. Why I say that is because grid search can sometimes take a lot of time, and I'll explain why. So with grid search, and we're going to do this example with decision trees, grid search is a way to do hyperparameter tuning. What you do with grid search, and all you have to do is import, let me see what the imports are here. All you have to do is import GridSearchCV. It comes from the model selection sublibrary of scikit-learn, and then you'll be able to use grid search. Now grid search has, I guess, 2 main parts to it. First, you have to give it the parameter grid. The parameter grid is a dictionary of lists that are basically all the parameters that you want to try out. So for example, in your decision tree, you have your 2 cost functions. You have your Gini or entropy, the criteria of which is trying to optimize. You have different max steps. Maybe you want to test all of these max steps. None is maximum max steps, if you all remember. How many samples you need to split, how many samples per leaf you need. And so when you're doing a grid search, you would usually pull up the documentation and see, all right, which parameters do I need to tune for this specific model? Once you do that, put the ones you want to tune into this dictionary. What grid search will do is it will test every single combination of all of these hyperparameters. So because of that, why I say I only expect you all to do it for 1 or 2 models is this can take a very, very long time. Right? If we're testing every combination of every parameter that we're tuning, you can see here we're doing, what is it? Threefold with threefold cross validation. So it's going to do each one 3 times. We have 2 criteria here, so it'll be 2 times 6 times 3 times 6, and that is the number of times it's going to train your model. So here you can see it's going to actually train your model 648 times. And it's going to be extremely computationally expensive. Usually what I recommend in like creating your parameter grid, start with a couple numbers, maybe like 3 each is what I like to do. And then you see like, you'll sort of be able to see what the best result is. And let's say you're testing 2, 5, and 10, and it says that your best is 10. You can pretty much, what I like to do is, okay, if the best is 10, let me take a look at 8 and take a look at 12 and just see like surrounding those, maybe you can find the best parameter. That's kind of my approach of how I like to do grid search. So I'm not searching over like 1 to 20 and it's gonna have to like search through many, many different models. So that's like a slightly more efficient way to do it, I think. So
Yush, one quick question. When you say that it's going to be computationally expensive, you mean to the collection of the data, or basically it's basically the time that is going to be consumed for running the data?
Both actually. So on one hand, you are going to be training 600 models in this particular case. You're going to be training 600 models, which is going to take a lot of time, but also it's going to be saving all of those models too. So because of that, it's also going to be very memory inefficient. So yeah, on both ends. Grid search is good because you don't have to copy and paste your instantiating your model with different parameters. It helps you basically do that all in one line. So we'll see in a little bit. But yeah, it does end up being computationally expensive. Usually what people do, they'll like set up a grid, run the grid search, go and get coffee, and then come back. That's what like me and my students used to do all the time.
So when we do that, like it's basically like, can we select which models to run? Specifically, let's say if we say that, okay, and we want models from, let's say, decision tree, or maybe we want models.
Yeah.
So can we select them from?
So for grid search works within your model. So for decision tree, you'll create a grid search. For like KNN, you'll create a grid search for that. For, I don't know, for random forest, you can create a grid search for that as well. So yeah, you would have to define your grid search per model. It's just different hyperparameters.
Okay.
Yeah, so grid search, really, really easy to implement, as with all the other scikit-learn things. First, you have to instantiate your grid search. And so it's with GridSearchCV. CV stands for cross-validation. You feed it in the classifier that you want it to grid search over. Feed it in the parameter grid, which was that dictionary of lists of parameters. Tell it how many cross-validations. Typically, because you're searching over all of them, 3 is enough. And then you can return the training score. And then all you have to do is fit it to your training data. I'm not going to run that because I'm not sure how long that will take, because it's running it 600 times. But what you can get from that is you can take a look at, so the mean training score, less important, but you can find the best parameter combination. So the best parameter combination, gridsearch.bestparams, will give you the best combination of parameters that got you the best test metrics for your data, which is pretty cool. So for that model and this data, for a decision tree, the best combination of hyperparameters is entropy, criterion, max depth of 4, 6 samples per leaf, and then 2 samples per split.
And that best scores, what are those based on? Do they have F1 scores or?
This score, I believe, is over the, I want to say, accuracy. Usually you will use that here. Let me see. Typically it is accuracy. Let's take a look at this real quick. So scoring, default is none. The estimator score method is used. And then the estimator score method for, let's see, for decision tree, scikit-learn. Oops, I want to see the documentation. Sorry, y'all. There we go. It is typically, I'm guessing it is, usually is accuracy. I'm not sure if they have it here, but typically
So
it
every
is
model has a
accuracy.
default decision score? I didn't realize that.
Yeah, it might be the cross validator, but yes. You see, like if you look at dot score, it gives you the accuracy. So I think if you look up, I think most of them should be accuracy, but let me look up a different one, for example. Yeah, let's do scikit-learn KNN.
And accuracy again is a true positive plus a true negative divided by all the.
That's right.
Oh, okay.
Yep. So score, yeah, mean accuracy of the test data. Yep. So grid search, these scores come from accuracy. Yep.
Very cool.
And then they also have the training and testing that is embedded in there as well, which is cool. So you can see here they're fitting the grid search. What they're doing here is they have the train scores, and then you're just scoring the test set on the test set. But yeah, this lab is here for you to do. I think it's a pretty good one to just get used to the setting up of a grid search. Pretty often you will be running grid search several times as well. So just keep that in mind. But yeah, that's pretty much all I wanted to talk about. This, I think, is just doing the same thing for a random forest. I think it'll give you the best parameters of, best parameters here. But yeah, you can do this for each model. But for your project, I really only expect it for 1, maybe 2 top models out of the vanilla models that you train. But cool, that's all I wanted to share for today. Any questions regarding any of this stuff? Or I guess like project that's coming up?
We'll be uploading this notebook, right?
Say that again?
Will you be uploading this notebook?
This notebook is actually the lab. So this notebook comes from your, oops. This notebook is from Ensemble Methods. It's literally the GridSearchCV lab.
Yeah, but then you have solved it, right? So
Huh? Oh, I
you
mean,
have solved it.
it is the solutions. I just ran the solutions.
Oh,
So
okay.
that's there. Yeah. Yeah, it's exactly the same as solutions. If you go into here, all of that, all of the stuff that is run is from the solutions.
Okay.
Yeah, I think for something like grid search, it's just like knowing the procedures of running the grid search. This is what I wanted to just like go over and make sure you all know. Well, cool. Again, highly recommend doing the mini project just so you have some experience running classification models before the project. During one-on-ones, we can talk about like what that's looking like currently, so I can give any feedback on if you're missing any steps. So yeah. Any final questions before we end off?
That's fine.
Awesome. So on Monday, we'll be talking about both SVM, support vector machines, which is our last classification model. And then I'll be talking about pipelines. And pipelines are really neat. Pipelines is basically like a way to aggregate the entire modeling process. You can do pre-processing, modeling, cross-validating all in one step. So that's going to be really cool to see. And that one we're going to just code out and just show procedurally what that looks like. All right, well, if there's no other questions, going once, going twice. All right, have a good rest of your night, everybody. And I will see you all at 101s or on Monday study group. Bye, everybody.
Bye-bye.